Okay, everyone. Everyone hear me? We're good? Okay. So, hi. Nice to see you all. So today we're going to be talking about web programming and data streaming in Haskell. I assume you know that already. We're going to get started actually with the Conduit half of this, which is the data streaming half of this. We're going to go through some of that. We're going to have a little stretch in between, and then we're going to move on to the web programming aspect of this. There are exercises. These are runnable exercises. Just to give you an idea of how they work, I'll jump over here. I told everyone, in fact, the commands are all up here. You can go ahead and you can install Stack and get your library set up, and then you can use the Stack script interpreter mode, which is you dump this thing in, whatever the contents are that I've got. You can dump it in a file, and then you can just run stack main.hs. Don't look at the code yet. I'll explain that part later. But you can go ahead and you can run it that way. This isn't necessarily intended to be interactive, but since everyone else is doing workshops, I figure some people here may actually want to be running the code along with me. So feel free to do so. Yeah?
What do we do if we already have Stack?
If you already have Stack, you don't have to install it.
Neither of those things?
No. You may have to do Stack upgrade if you've got an older version. I'm using a newer feature.
There's a repository?
Oh, that's right. Yes, you can actually just go to, it's all inside the slides. So go to snoyman.com/reveal/conduit Yesod. Everyone's free to guess why it's called reveal. Yeah. Does someone have a question? No? Okay.
It's called Reveal?
No, the URL has reveal. I'm using reveal.js because JavaScript is awesome.
Oh, sure. I was using it for my talk, too.
The repository.
I just turned off the transitions.
What? There's no repository. What?
There's no repository?
It's not a repository. It's a URL.
Great.
It's a page. There's no repository to clone. Okay. Cool. So we're going to talk about these two different libraries. This is going to be about how to get things done, and the goal is to really get you guys to the point where you understand the concepts behind the libraries, how to poke at them, and how to get started. You're not going to be able to go and write a Yesod application at the end of this without looking up the docs. In fact, I can't do that. I have to look up the docs too. So don't feel bad if you don't understand the entire surface area of Yesod or Conduit after this. It's big. The goal is get the concepts, understand how the pieces fit together, and you're able to do it yourself later. There's lots more information. There's a tutorial for Conduit available online. That's got exercises and other things. And there's a book for Yesod available online. So if you want to go ahead and learn more about these things afterwards, those are the links. And feel free to ask questions in the middle. If we start running out of time, I may push them to the end, but please do. Here are the instructions. The instructions are already up here. And yes, this will take a long time to install every single library. It's a little bit of overkill, in fact. Okay, so we call this streaming data. And I hope at least a few people here are wondering, what is streaming data? Because it's not exactly like there's a clear definition in the world of what we're talking about. So what are we talking about in this case? Well, everything is typed in Haskell. So we're going to be talking about types in order to make this work. So streaming data means that we want to do something like processing a sequence of values of some type. Or we want to produce a sequence of values of some type. Right? The point of this is we don't want to keep all of the data in memory at once. So let's talk about files. Files are a good example for this. We may want to go ahead and open up a file and produce a stream of all of the bytes that are in that file. Or we may want to take a stream from our application and we want to stream it into a file to create that file. An alternative would be to just create a massive memory buffer and read the whole thing in. And if you've got a 50K file, that's not a big deal. And if you've got a 2 terabyte file, or if you're reading something over a network, which could go on infinitely, this is a problem. So this is where the streaming data problem kicks in. We also have laziness in Haskell. I'm sure most people are familiar with the basic concept that we have laziness. We don't actually have to read an entire list into memory in order to have a big list. We can have a 5 gigabyte list that actually only takes up a small amount of memory. So why do we need Conduit if we already have laziness? The answer is laziness doesn't actually allow us to perform side effects, such as reading out of the file system, in between each one of these chunks. Technically, you can because of lazy I/O, and I'll explain why that's a bad idea. But good, pure laziness doesn't allow that. Conduit allows us in a nice way to deal with those interleaved side effects. Another thing that I'd point out is a lot of people think, oh, I'll use that in some weird corner case where I have a streaming data problem. I would argue that streaming data is actually a much more common problem than people realize. It shows up all the time, and I'll give you some motivating examples in one of these slides. I don't remember which. All right, so we've got Conduit. Why would you want to use Conduit? We have lazy lists. I just talked about that. They don't have interleaved effects. What about lazy I/O? We're not going to go into the details of what exactly lazy I/O is, how it works under the surface. What I will tell you is, if you use lazy I/O, you've got two big problems. Let's say you're reading, again, I'm going to use the read file example because it's a really nice example. You read a file with lazy I/O. Now, as you begin processing on that file from your pure code, you have the potential to trigger an exception. This is exactly the opposite of what we want from Purity. We are performing I/O, it has side effects, it's partial, it's bad. It's a nice hack. It works very conveniently in many cases, but it's not, but we're exposing ourselves to a lot of surface area of risk. The other problem with lazy I/O is we get non-deterministic resource consumption. That might sound scary. What's going on is when you call read file with, let's say you do a strict read file. What it's going to do is it's going to open up the file handle, it's going to read all the data out of it, and it's going to close it, and then it's going to give control back to your application. If you do it with lazy I/O, it's going to open up that file handle, and it's going to keep that file handle open until you fully exhaust everything in the file. If you never fully exhaust the contents of the file, you don't know exactly when the file handle is going to close. The garbage collector eventually will kick in and close it, but that's non-determinism. If you're, say, for example, writing a high-performance web server, and you want to be able to handle tens of thousands of requests per second, it's possible that you will end up running against the open file descriptor limit. So this is a problem. There are alternative libraries. The point of this talk is absolutely not to try to convince you which streaming data library to use. We can have conversations about the differences. But since it's such a common topic, I do want to give everyone a little bit of an intuition about the two most common alternatives I see people talking about. So pipes is another library. It's very similar, in fact, to Conduit in its structure, though the way you end up using them is pretty different. One of the big philosophical differences is that pipes really focuses on correct referential transparency, correctness by around a category instance. And as a result of that, it ends up pushing off some kinds of programs that you'd want to use to higher layers in the stack. So the pipes parse package is what you end up using for some kind of parsing, as opposed to in Conduit, where you would do that with the core Conduit package. So some people like one, some people like the other. It's a different approach to things. The streaming package is another one. Probably the biggest thing that I see people talking about with streaming is the fact that it has nice support for substreams. They use this, I think they use a free monad approach, free monad transformer approach for substreams, and so it's easier there. We have approaches for it in Conduit. You could argue about which one is better. And then other things are easier in Conduit. You'll see an example with what we call zip sync. And that's something that's, as far as I can tell, it's significantly harder to do in streaming. Don't use lazy I/O. Please, just don't use lazy I/O, get away from it. If you're writing a toy application, fine. Any kind of production code, you should be trying to get away from it. That's what I want to get across. If I get anything across in the Conduit half of it, it's that. Figure out something better to use. Lazy lists are fine, but again, we'll have to figure out what the limitations are. All right, so let's look at some real common use cases that this would pop up in. I've already talked about reading and writing with files, or communications over a network, over a socket. Another one, reading data out of a database. You've got a database, you've got a table, you want to pull out 1 billion records from it. You definitely don't want to pull it all into memory at once. This is a streaming data problem. Here's one people don't think about a lot. Let's say you've got a directory structure. You want to look at 1 million files in a directory tree. You've got a deeply nested directory tree. This kind of problem is very well suited for streaming data. If you use standard library functions from like the directory package in Haskell, you're going to end up pulling in a huge number of file names in memory at once. This can actually be crippling for some applications. Another example, you want to implement a job queue. You don't need a streaming data approach for this. You can actually, in fact, for all of these things, you don't need to use a streaming data library. You could implement a job queue by hand. You could go ahead and you could use a tchan, and you can play around with that manually. It can be very convenient, though, to use an existing streaming data library and abstract over where your data is going to be coming from. Instead of hard coding it to a tchan, you could have a data source that comes from anywhere. And then it's easier to test it, And you're able to use a lot of combinators that already exist instead of writing them yourself. An example we will see in the Yesod half of this is, let's say you want to generate a large HTTP response body. This could happen. You want to go at, let's tie it together with databases. You're pulling out 1 billion records from a database and you're converting it into a CSV file because everyone loves CSV files. So you're generating the CSV file in some weird character encoding or something like that, and you go ahead and use Conduit and you can generate this response body in constant memory. And parsing, that's we have great parser libraries. Turns out that these parser libraries like AutoParsec, they have built-in streaming support, but it's a little bit clumsy to use. When you put AutoParsec together with Conduit, it's trivial, for example, to write an XML parser, take an XML file or an XML HTTP response body, and pipe it through Conduit and do stream processing, which, if anyone's done SAX parsing in Java, firstly, I feel sorry for you. And secondly, this is a hell of a lot better because some types are awesome. All right. Conduit is not a solution for every single problem. So if, for example, you have a very highly optimized CPU pipeline, you have to do some kind of tight inner loop, you can't afford any kind of overhead, Conduit is not your library. Conduit does introduce overhead. I'm not going to show it to you here, the implementation of Conduit, but the implementation of Conduit does use heap objects. So as a result, each time you step through it, it's going to allocate a heap object. For a normal use case of Conduit, which is very I/O heavy, this doesn't matter. The amount of allocation you're going to use is going to be dwarfed by all of the I/O you're doing, so it's fine. If, however, you're doing something in pure code that could have just been, an unrolled loop in C, guess what? Conduit is going to be a hell of a lot slower. Vector would be a good use case for that. If you're really stuck doing it, you can write, a loop manually. There's other approaches that exist. If you don't have any kind of interleaved effects, in other words, if you're just doing pure code, feel free to use a list. I have actually had use cases where I've used Conduit in pure code because I thought it was more convenient than using a list. It does exist, but generally speaking, it doesn't make sense. There's no reason to add that overhead. Just use the right tool for the job, and Conduit isn't the right tool for the job in that case, unless you happen to be someone like me who loves writing Conduit code. And then basically any other problem out there, Conduit's not going to solve. Don't even bother. If you have some type theory issue, just avoid it. Conduit has nothing to do with that. All right, we can finally look at some code. This is a fold. In fact, in this case, we're just going to sum up the numbers from 1 to 10. This is pure operation, so this obviously could have been done with a list, and it would have been fine to do it with a list, but let's get a little bit of an introduction. We have yield many, which is going to yield, as we'll see what that means a little bit later, the numbers from 1 to 10. And then we're going to pipe that in, we're going to fuse it, in fact, is the term, to sum C, which is exactly like the sum function, except it works on conduits. So you can start to see a little bit of the naming. We're sticking C at the end. We're going to run this. We're going to run this purely, meaning in the identity monad. So there's no side effects. And then we're going to print the result. Let's look at another Hello World example. Copying a file. I keep talking about files. This is a real example. First, I'm just creating a dummy file. I'm using this. I'm not going to make fun of string-based I/O right now. So we go ahead and we create a file, and then we're going to copy the input file to the output file. This is it. We're able to declare that we have a stream of data. From here, we're going to fuse it together with the sink of data that we're sending it to, and we run Conduit. And you may be wondering, what is that res at the end? Res there is for resource, and it means that we are allocating some resources inside. We're guaranteed that this is exception safe. If any exceptions get thrown in the middle, all of the file handles will get closed. That's good stuff. And this is, I would argue, and I've written this in other languages, Java, for example. It's a hell of a lot more painful to do all of the looping, all of the management manually, instead of just letting a library handle it for you.
Question?
Yeah.
So, another example, I know you said let's handle the exception safety, but if there's an exception and we have to say print something to the user.
You would handle that outside. You could handle. There are exception catching functions. You could use that. You could do it inside of Conduit. Usually, what I found is it makes the most sense is at the end of the day, this is all getting converted to I/O or something else. Once you're back at the I/O level, that's usually when you want to just go ahead and catch exceptions and deal with them.
So, for example, in this case, the input
Yeah, so you could go ahead and you could put a try here, or try any from the summit. Use the safe exceptions package, separate issue. Yeah, so you could use try any there, and then you could deal with it. Alternatively, if you wanted to know if this file doesn't exist, you could use what's called, you could use catch from the, also from the safe exceptions package actually, and you could catch it inside. Yeah. All right. And one last example. So far we've only seen this idea that we're going to have a source of data and a sink of data going from one place to a destination. Conduit is much more powerful than that. It has the ability to transform data along the way. So in this case, this is not too different from the first example we had. Again, we're going to have a source, which is the numbers 1 through 10. We're going to have a sink. This sink is creating a list at the end of the day. And in between, we're mapping. And this is just like the map that you would always use from lists. So hopefully the intuition here can transfer that all the list functions that you're used to basically sort of kind of translate directly into Conduit. If they have the same name, if the function exists, it's going to be the same thing, possibly with different runtime semantics, but it's going to be semantically pretty similar. OK. So now let's actually dive in and understand the terminology. Actually, getting the terminology is probably the biggest part of the battle. Once the terms, once you get the terms, the rest of it kind of fits in. So as a motivating example for all of these, let's consider this bit of Conduit code. Foo, baz, we're piping these things together, we're fusing these things together, and we call run Conduit on it. When we put these all together, we call it a pipeline. So we have a pipeline of data. Inside the pipeline, we have a whole bunch of data streaming in and out and going from one thing to the next, like we're going to show. But the pipeline as a whole actually has no data coming in or going out of it, so it's self-contained. And then we're able to use run Conduit to extract values out of it. Foo, bar, and baz are individual components of the pipeline. So these things do actually have data coming in or going out of them. And then we're able to connect them together. Another piece of terminology, you'll see that foo is fusing together with bar. The way we say this is that foo is upstream of bar, and that bar is downstream of foo. You can say the same thing about bar and baz. Bar is upstream of baz, and baz is downstream from bar. You may at this point be looking at it and thinking, this kind of looks like Unix shell stuff with pipes. That's intentional. The same way, if you get rid of these dots, and you're on a Unix shell, this would be saying run the foo process, take all of the output from foo and pipe it into bar, and then take all of the output from bar and pipe it into baz. You now understand Conduit. That's exactly what Conduit's doing, nothing more, nothing less. Yeah?
So we can assume like the order of values from left to right and not right to left, like in function composition?
It's slightly more, well, yes. Yes, it's different than function composition in that sense. The order in which it evaluates is different. We'll get to the order of evaluation, but as far as conceptually where the data is flowing from the left to the right. So yeah, it's based on, it is different than function composition. It is like Unix pipes. Okay. Another piece of terminology to pick up is that when we say that bar is downstream from foo, we can also say that foo is able to yield downstream to bar. This is actually a function name in Conduit. You can yield a piece of data downstream. Anyone here familiar with Python generators? Few? Okay, that's where the name comes from. It doesn't really matter. You don't like go off and learn Python in order to understand this. Not worth it. But that's where the name comes from. Similarly, baz is able to await for output from bar. So that's at the low level, we're dealing with really two functions: yielding downstream, awaiting from upstream. And finally, you're able to run this pipeline using run Conduit. You run the pipeline in order to perform the effects, whatever. Remember, we kept talking about interleaved effects. So we're going to perform whatever effects have to happen, whether it's writing to a file, pulling from a database, anything else. And then finally, extract a result. And we'll talk a little bit more about results. Not yet, in a later slide. So fusing. We talk about fusing two components together. Right here, we're fusing together foo and bar. This is now its own component. This is very much like function composition. You can take two functions, you can compose them, and you have a new function. It's built up of simple functions, and then you make more complicated ones. Same thing in the Conduit world. And then, so once you go ahead and you fuse these two things together, this combined conduit, this combined component as a whole is feeding data into BAS. And you could also look at it alternatively. You could say that bar and BAS, it's associative in other words. Bar and BAS are fused together into one component, and foo is feeding data into them. Whichever way you want to look at it doesn't matter. It's all the same. Streams. I've already said this word a lot, so you guys probably have picked up on it by now. Foo is creating a stream of data. All that data is going to have the same type because we're Haskell and we have strong typing. So foo is going to create this stream of data. That stream of data is going to flow into bar downstream. That's what the name is. And again, you yield to downstream, you await from upstream. And results. So if you remember way at the beginning, we had sum C. We said it's a fold. At the end of the day, a fold produces a single value, right? If you take a list and you sum the list, you started off with lots of values and you've condensed that down into one value. Well, that's exactly what a pipeline does. Whatever's going on inside the pipeline, at the end of the day, you are going to have one value that pops out of this whole thing. The value is going to come from the most downstream component. So if you go ahead and have some values coming out of foo, they're coming in the stream from foo. And they're coming in the stream from bar. BAS is not going to produce a stream of values because there's nothing to send those values to. Instead, it's going to have a single result value that you get when you run the conduit. You may be wondering, oh, well, what happens if bar wants to return some result value that I want to see? There are helper functions. That's a more advanced case. It almost never happens, but there are helper functions that allow you to do that too. All right. So now we've got a pipeline. So we've talked about all these components, and we fuse the components together, and we connect the streams together like Legos, and we finally get this thing that has nothing coming into it and nothing going out of it. We've got a complete pipeline. That's what it means. It means that there are no streams anymore. They're done. You'll see the types a little bit later. We talk about the input to this pipeline being the unit value, the parentheses. And the output is this type called void, which has no values that exist in it. You may be wondering, why is there a difference between these two? Good question. It's not worth getting into it. It's probably a historical accident. Those exist too. So you can basically just ignore the fact that one is unit, one is void. The point is, nothing happens. There's nothing going into it. There's nothing coming out of it. So let me ask people a question. If you're looking at the individual components of the pipeline, and you understand fusion, and you understand the streams, what is the input type that's going into foo? Who can take a guess? Louder? Unit, exactly. Why did you know that it's unit?
Generating the stream.
Well, it's generating a stream, and it's composing together into a complete pipeline. If it's turning into a complete pipeline, starting off with foo, then this is going to be the most upstream thing in that pipeline. Similarly, BAS is going to be producing a stream of what output type? Void. Good. This is something to just keep in mind. Whenever you're putting these things together, whatever you have on the far left has to have an input type of unit. Whatever's on the far right has to have an output type of void. And foo and bar, their outputs and inputs need to match up with each other. Okay. So now we know how these things fit together. Let's talk about how we run them. Because the execution model does matter, because unlike lists where we don't really care how it's going on under the surface, here we're actually interleaving effects. So the way in which these things get computed matters a lot. So conduit execution always starts at the most downstream value. Sorry, downstream component. So in this case, we'd start off at BAS, and then we'd move up. We're going to keep processing inside this component until it awaits. And awaits is where it says, upstream, please give me some value. At this point, execution completely halts inside this component. So if we're talking about sum C is going to say, hey, I can't get started until you tell me what's going on. Give me a value. Sum C For all we care about now, it ceases to exist. It's sitting off to the side, minding its own business, has no control. It's not executing anymore. Control now gets passed upstream to the next upstream component. It's going to do its thing. It itself may also await, in which case we go upstream again and again and again until we get to the end. Finally, we're going to get to somebody who is going to yield. It's going to send some value back downstream. At that point, execution stops there, and this guy that went to sleep over here is going to wake up, take control, and do its thing. And we just keep bouncing back and forth between all of these different things. If you have a whole bunch of components, one of them is going to be in charge at any given time. Now, when you call await, you are always going to get a chance to run again. Point being, you can await and ask for a value from upstream, and upstream may say, sorry, I don't have anything left, right? You're reading out of a file, you say, hey, please give me another chunk, and the file says, I'm empty. So you may get a nothing back, in which case, you can go ahead and you can clean up. In the case of sum C, you'll go ahead and you'll return your result value. You've been keeping a total, now you're going to return it. Yeah?
Is now a good time to ask about concurrency? While you're talking about execution, or do you want to do it?
Let's do it at the end of the Conduit slides. Concurrency is a complicated topic.
Yeah, because I use Python.
Yeah. Okay. By contrast, upstream doesn't actually have the ability to always get control back. When you're in a conduit and you yield, there's a possibility that you will never get awoken again. And this makes sense if you think about it. If no one ever says, hey, I want another value, why are we going to even talk to you again? You may be worried about this. What happens if I'm reading from a file? I'd like to be able to close that file when I'm done. How am I going to be able to close the file if no one ever wakes me up again? We have something called finalizers, and you'll see that in a moment. All right. These are the types of conduit. The main type is called conduit M. Again, historical accidents. The main type is called conduit M. And it takes 4 type parameters. This is probably the thing that people hate the most about this library, is that it's got so many type parameters. Believe it or not, this is many less than we had originally. So we've got 4 different types. Who can take a wild guess what I stands for? Anyone? Input. You guys are awesome. O, anyone? Output. M. And R? Result. Okay. You guys got it. So you can imagine, if you have foo here, it is consuming a stream of unit values. It's producing a stream of A. I'm just using up some type variables here. What does this M mean? I didn't actually highlight it. What does this M mean? Very good. This thing is able to run effects in the M monad. This could be the identity monad. For those who don't know, identity is just a fake monad, basically. It's not going to be able to do any kind of effects. It's not a fake monad. But it can't do any kind of effects. Or it could be I/O, and then it's able to do effects. Or it could be ST. It could be any monad. The point is, Conduit doesn't actually have any kind of connection to I/O. It happens to usually be used for I/O, but you could throw any kind of type in there. Or you could use a monad transformer stack. You could do whatever you want. Point is, once you're inside Conduit, you have access to be able to perform all of these different things. And almost every single real-world application of Conduit is going to be doing that. Again, I'm going to go back to source file and sync file. Every time you're going to open up that file, that's an effect. That's going to be in I/O. Then you're going to read a chunk out of that. That's another effect, and so on. Yeah?
So each conduit or each component is of this type, right?
Yeah.
So there's output, there's also result.
So it's not a result. We're just giving, I mean, you can call it that if you want to. We're just calling it different names to make it clear. Output is a stream of values.
Okay.
A result is a single value at the end.
So what happens to those values that are produced in the middle of the pipeline?
So you're saying what happens to the result value that foo generates? It's not allowed to. It always has to generate a unit value.
Okay.
Unless you use, again, I mentioned it, I don't want to get into it. There's something called fuse upstream where you're able to capture that value.
Okay.
But that's an unusual case. The normal case is the type system will stop you from generating values upstream. Okay, so now you can see how this type Tetris starts to happen. Now we've got this bar, and bar takes in a stream of A values, produces a stream of B values. That's why we're able to put foo and bar together. And when we put foo and bar together, we have the A disappears, right? A is now fused in the middle. You can never observe the fact that there are A values bouncing back and forth between these two components. It's irrelevant. It's an internal detail. But the input to foo still survives as the unit here, and the output from bar still survives as B here. The monad has to match in every case. And this unit value is the unit value that comes from downstream. In this case, in the case of foo and bar, you can't really see it because both of them had unit. But in the case of bar and baz going together, you can see that we've now captured the R, which is the result value of baz. Yeah?
Going back to Unix, could you draw a comparison between O being the actual like standard out and standard in, I and O being standard out, standard in, and then R being like an exit code or something?
Oh, that's an interesting. I actually couldn't figure out an R. That's a really good example. For people who didn't hear. So we've got, if you're on a pipe, if you're on a shell in Unix, you are going to already have standard input and standard output as part of the terminal. When you run a pipeline, when you run a single command, your input is going to go into that command and the output is going to go back to the terminal. And if you put together a pipeline of these things, then your input is going to go to the first thing. You're going to go through that pipeline in the middle, and on the other side, it's going to come back out to your terminal. So this is very similar to what's going on here with Conduit. The result value is like the exit code you're going to get from running those processes. I don't know what happens if you have an exit code from only an error code from only one of the, or an upstream one. I don't know which one survives.
If it's the whole pipe.
Oh, it does?
It's supposed to. If it's non-zero.
Okay. Okay.
Yeah.
All right. Fair enough. So I guess it's slightly different in the case of Conduit because it's always going to be the downstream one.
Yeah, it's not matching actually.
Yeah, but it's close. Okay. So after we go ahead and we put these two components together, we can go ahead and put all three components together, and now look at the type of this. This type is taking in unit, producing a stream of voids, and returning an R. Hooray, we have a pipeline. That means we can run Conduit on it. And when we run Conduit on this, we get a monadic effect with that result value. And that's it. Now we're out of Conduit land. It's as if that Conduit doesn't exist anymore. We're just back to normal simple monads, because everyone thinks monads are simple. We also have the run Conduit pure, in which case we're going to run that monad immediately and it's going to disappear, and run Conduit res we'll explain later. Yeah?
Is there a way to turn something like foo bar into a runnable pipeline?
Yes. Okay, so interesting question. What would you do with the stream of Bs that come out of it?
So I'm just thinking in terms of composability. I have a pipeline, but
No, but I mean, you can do it. You absolutely can. The question is, what are you doing with that stream of values?
You can't run it. You have to have something that.
well, I can put something else at the end.
Well, so then you have a pipeline. So you can put anything at the end, and there are two common examples you could do to make a type check. You could either put something at the end that does nothing, in which case you have no pipeline, because the downstream, we'll actually see that in a sec. The downstream in that case is never actually demanding a value, so the rest of it isn't going to run. Or we have something called sync null, which is like dev null, if you want to use the Unix comparison, in which case it's just going to grab all the values and throw them away. And then you can go ahead and do it. We could actually theoretically relax the type of run Conduit so that it just allows all of that to happen. We don't want to do that because that's throwing away type safety. You could accidentally throw away values. It's much better that we're explicit about the fact that you're throwing away data.
For you though, it sounds like you wanted to compose, so you can always compose them however you want, and then before you actually do the run Conduit,
Yes,
that's when it's important. You can compose all you want before you do that.
Yeah.
Yeah, well,
Yeah.
each segment is a pipe, but only when you've got all together in that pipeline.
Yeah. Yeah. Okay. Is everyone with me so far? I think everyone's getting this. Yeah? Okay. Let's look at some real, actual things that exist in Conduit. Just because the slide, I didn't want it to be ridiculous, just assume that the type signature has a monad M constraint in every place. So we've got map C. This is the map for Conduit. Oh, and I highlighted the wrong thing again. Oh, suck. Okay. This thing is going to take a function from input to output, and it's going to generate a conduit that goes from I, the input, O, the output. Will actually work in any monad. Notice this. Since over here we have no monad specified, it's going to work in any underlying monad. And then it's going to return a unit value. You might be wondering, why can't it return something else? Question would be, what else would it return? It's not actually producing any kind of meaningful result. Yeah?
So if you try to run the conduit inside a new block with the monad, you use type inference for it to figure out which monad to use?
Yes. Yeah, type inference will kick in. And another thing you can do is you can combine these pure conduits like mapc with impure conduits like mapm, which do perform side effects, and then the effects will only kick in for whichever parts of the pipeline actually do the effects. So you can actually have entire pure pieces of the pipeline, and then do your I/O stuff. Just in, for example, you could do source file, sync file, and in between everything else could be pure.
When you're running this, you're going to get the value out automatically, like with do notation with left arrow, finding to something else?
Yep.
Okay.
Yep.
Would you like to repeat that?
Say again?
Would you like to repeat that?
Oh yeah. So, thank you. So the question was, when we're actually using this, would we go ahead and at the end of the day just use do notation or use a monadic bind or something to grab the value out of it? And the answer is yes. That's exactly the way you would end up using this. Okay. So we've got a map C. This is transforming data. Fold LC. This one is consuming data. It's a normal fold, a left fold. There's no such thing as a right fold in Conduit. Because we have streaming data, we can't actually start at the right side. We have to start at the left side because that's the way that the stream works. And this is exactly the same type signature you would have, for the first two components when you're dealing with a normal left fold. We're taking some input, we're combining it with some starting value, and that starting value eventually will get spat out as the result. That type will get spat out as the result. Notice that O and M never appear over here, so we don't have anything to say about them. Okay, mapmc, mapm_c. We're going to run a monadic action on every single thing that comes to us from upstream. Repeat C, we can create infinite conduits. This one is going to create an infinite stream of values, the value O, and just keep sending them downstream. Yeah?
Yeah, for like mapmc, why does it have an O if it doesn't output anything?
Good question. So what would be the alternative? What could we put there instead of O?
Unit or whatever the...
Right, so we could put unit or void instead. That's a good question. So why is it that we put an O here instead of making it more monomorphic? We know for a fact that this thing is never going to produce any kind of values. The reason is you can actually monadically compose conduits together. We've only looked at fusing them, but you can go ahead and you can sequence these things together. And in that case, you want your types to be as general as possible. Because even though mapmc is never going to send anything downstream, you may want to stick it together with something else that is going to send something downstream. And we'll see.
Pass this through then?
We also have pass-through, but that would be different. We'll see a little bit of an example of it. But the point is, the more general we keep our types, the more composable we're able to make things. Okay, take while C. We're able to go ahead and limit the stream that we're going to send downstream. So in this case, we're taking some input value, and if it passes the predicate, if it returns bool, then we're going to send the values downstream. Notice here, we're taking an input stream of type I, and we're returning and we're sending out an output stream also of type I. It has to match. And decode UTF-8C is an interesting one. Here, we're able to go ahead and take a stream of bytes, like you might read out of a file, as byte string. Oh, sorry, I got the types wrong here. Oops. So this is supposed to be conduit M byte string text M unit. So sorry about that. Point is, it's going to be able to take in a stream of bytes. It's going to produce a stream of text. But let me ask you a question. What happens if the file isn't actually UTF-8 encoded? In that case, we're going to go ahead and we're going to throw a monadic exception using monad throw. So some of the functions in, we actually have a number of functions in Conduit that have some kind of monadic constraint on them. Monad IO would exist for something like source file, or monad throw for something like this, which is actually pure, but it could fail. Yeah.
So if you have multiple of these things that can throw exceptions, catching them outside,
Yeah, you can.
you probably didn't use the context, right? You may want to catch them.
You're free to catch them inside or outside, however you want. Okay, that's it. No. Okay, fine. So you guys do actually at this point really know all you need to know to go and look at the functions in Conduit. You'd be able to play around with it and understand it. But let's actually look at some examples, because otherwise, what was the point? So we've got a function here, loud yield. Loud yield is going to be just like yield. It's going to send a value downstream. But every time it sends a value downstream, it's also going to print out a message to standard output using just normal putstrln. So we're going to go ahead and use this pipe together with loud sync null. So this is the sync null I was telling you about before, except it's also going to tell you every single time that it awaited. Who can guess what our output is going to look like from this program?
Void.
Void? Why void?
Oh, wait.
Say again? I can't.
Well, no.
Think about it for a little bit. Remember the way that it executes.
Awaited.
So it's going to awaited. So you're saying it's going to jump back and forth between awaited and yielding, awaited and yielding? Or is it going to have a whole bunch of awaiteds and a whole bunch of yieldings? In other words, is it going to group these things together, or is it going to interleave the two things together? Interleave, I kind of gave that one away, didn't I? Yeah, it is. And this is exactly what we want. So let's go back and look at how it's working. We start off in loud sync null. Why do we start there? Because we always start downstream. So now we're in the downstream component. We're going to await for a value from upstream. Why are we going to await? Because that's the way that this mapMC is implemented internally. So it's going to await, meaning it's going to now give up control and pass control to upstream. Upstream is now going to enter this loud yield function. The first time, it's going to print out its message, and then it's going to yield. And when it yields, it gives up control and immediately bounces back downstream. Now that we're downstream, this thing is going to finish its await, receive the X, and it's going to print out a message. And then it's going to loop and do it again. And that's why it's going to bounce back and forth. If we did this any other way, we would have to hold a whole bunch of values in memory. And we're only looking at 3 here, but imagine that this was in fact 1,000,000 values. If we didn't have this interleaving, then we would have had to hold on to 1,000,000 values in memory at once, which is exactly what we don't want to do. So the fact that we see this output proves that we're actually doing things in a memory efficient way. Yeah?
How come you actually don't need the rank n types language extension like you're using explicit for all, right?
You're saying why don't we need rank n types?
For your type switches, you've got for all. Is there a reason why you don't need to have a language extension?
That's a good question. I may have just modified the slides after some feedback. Yeah, if anyone runs it and it doesn't work, you can either take, the for all isn't actually necessary there.
Well, I don't think it can infer types without it.
No, if we took off for all, the code would work. Yeah. Say again? I'm gonna skip it. Okay. So that last example didn't actually show us using the await function at all. We just implicitly used it. Let's go ahead and play around with await so we get a little bit of a feel for it. So now we're implementing the exact same function we had before. We had a loud sync, but we're going to do it manually. We have to do some kind of a loop. So we start off with loop because I like to name things simply. So we have loop, and we're going to go ahead and we're going to actually be a little bit louder than we were before. I should have called this louder sync null. So now we're louder. We're going to go ahead and we're going to print out that we're calling await. We awaited. Control is going to stop here. It's going to pass upstream. And then we're going to come back and we get a maybe value. This maybe value is, if it's nothing, that means that upstream is completely terminated and it has no more values and it will never ever give us a value again. If you keep calling await, you're crazy because you think something is going to change and things don't change. If it's a just value, then we're going to go ahead and we're going to print out the value we got and we're going to loop again. And this is what the output of this looks like. It's going to call await, it's going to yield, that's the upstream bit, and then it's going to receive and start again. Make sense? Let's say that we actually don't do any awaiting. Let's say we have a source that simply prints out a message and a sink that just prints out a message. Look at the output that we've got here. It looks like the source was never called. Why not? Who has any idea? Never awaited. Exactly. If downstream doesn't await, then the upstream never gets called. There's no reason for it to ever get called at all. It's ignored completely. All right, let's play another output guessing game. Look at the code, have a little fun. Sync 1, say again.
Source 1, sync 2.
And why not source 2?
It gets called wait again.
Good. Did everyone get that? We're going to hit sync 1 because we're downstream. We're going to hit await. We're going to bounce up here. We're going to hit source 1. We're going to yield. That's going to bounce us back down here. We're going to do sync 2, and then we exit. By the way, if anyone's curious about how this is all working under the surface, Conduit is based on top of coroutines, which if you already know coroutines, it may explain a little bit about why this behavior of bouncing back and forth makes a lot of sense.
So source 2 never gets outputted?
Source 2 never gets outputted. We get this far and no farther. Okay. Let's motivate this a little bit farther. Let's play around with undefined. Who can guess what the output of this, not the output of, who can guess if this program throws an exception or doesn't throw an exception? Good, it does not throw an exception. We hit this return, we never even bother looking upstream. We can have anything including undefined upstream of us, it makes no difference at all. What about this one? Same thing. It doesn't matter that it's in between these two things, right? So this whole thing composed together is also undefined. Doesn't matter because it's just return is just downstream from it. What about this? Exception. Because we're immediately going to try to enter that sync, that downstream component. It's going to be undefined. It's going to fail. Finalizers. I mentioned this way earlier when I was talking about source file. Who can guess what the oops, I put the output in this one, sorry. Okay, you can either ignore that and pretend you're really smart and tell me that what the actual output is. Okay, let's try to understand though why the output is exactly what I put at the bottom. So print C is a conduit that consumes everything from upstream, turns it into a string with show, and sends it out to standard output. Pretty straightforward. Take 2 is going to demand only 2 values from upstream, and sorry, it's going to demand only 2 values from upstream, and then it's going to stop running, and source is going to do this thing. Source is trying to yield 10 values. So why is this going to be the output? It's going to clean up after because we have something called yield or. So actually, sorry, let me back that one up a second. So we have print C, that's going to demand a value from upstream. Take C is going to demand a value from upstream. We're going to go into source. Source is going to run for the first time. We're going to do acquire some resource. We're going to print that out. And then we're going to enter this map M over the numbers 1 through 10. First time around, it's going to yield or. Ignore the or for just a moment. If this just said yield, we'd yield 1 downstream, and we would bounce back here. Take now gets that value, and it itself is going to yield it downstream again, send it to print, and we get 1. I don't want to have to say all that stuff again. We do the same thing with 2. We get to take, it goes down, awesome. Now print asks for another value. Take says, I'm not going to give you anything else. Even though there's more stuff upstream, that's the contract that take is giving you, so it doesn't run. If we didn't have this yield or, if it was just yield, control would never get passed back to source. It would have no way of saying anything at the end of execution. But we actually want to tell the user that we're cleaning up, or we actually want to close a file, or something else along those lines. We want to commit a database transaction. So we have yield or. Yield or says, I'm giving this value, or if you never want to talk to me again, run this action. And that's a cleanup, or a finalizer.
Doesn't take have to do something special to let the source know about it?
Say again?
Doesn't take C doesn't have to do something special?
Does take C have to do anything special? No. This is all handled by the internals of Conduit. This, by the way, is an example of where Conduit and pipes would disagree about how to do things. Pipes would say this should be handled outside of pipes, outside of the abstraction, and Conduit says this is so common that we should just throw it in. So this is handled internally by the fuse operator itself, actually. Yeah.
How does source know that it's not going to await later or?
Oh, it might. It might. So it's passing that function downstream. And if there's another await from downstream, that finalizer is going to get thrown away and a new one will be generated next time. But, correct, but there's no way for it to know whether it's going to get called in the future. Every single time it gets called, it's passing that finalizer as an option that it's going to get run.
So who decides the option?
Downstream. So when basically it's actually the run conduit bit, basically. At the point when run conduit hits, any finalizers that are still active are run. Yeah?
Is it possible to have more than one downstream? Like four?
You mean like you want to consume a single stream by two different consumers? Yeah. Yes, we have an example.
In that case, it would only clean up after the last one.
Correct. You could actually have different semantics. You could have, I'm only going to clean up after, like the same way that like in the async package, if you're familiar with it, we have race and like we're going to just wait for one. We could do things like that, but the standard is, yeah, wait for both of them to finish and then clean up. Okay, this is all well and good. And we've got finalizers and everything gets cleaned up quickly. What about this? Almost exactly the same. The only change that I made is that I put undefined after the print C. It's going to call an exception. Is it going to call that exception before or after we trigger this finalizer?
Print the first value.
Say again?
Will it print the first, show the first value and then fail?
So, well, it's going to print both values, actually.
Oh.
It's going to print this acquire some resource, because it has to do that first. It's going to print the first two values. Take C is going to be done. So print C is going to give up. Print C is going to say, I have no ability to get any more values. I give up. Whoever wants to take over next, go ahead. And we've given that over to undefined. So undefined is taking over, and it crashes. At no point in this did we actually get a chance to run the finalizers yet, because the finalizers only run when we hit run conduit. As a result, this finalizer never gets run. That's not too bad here, but imagine that we were trying to close a file handle. Point is, this is not exception safe. This is a big problem because we want to write exception safe code and we can't do it. Which is why we have resource T. Resource T is a mutable variable. It's evil, it's terrible, it's mutable, it's all the bad things in the world. But it's a mutable variable that keeps track of finalizers. It keeps track of cleanup actions. When you do run conduit res, the contract that you're getting is when you register a cleanup action, we will make sure it gets run even if an exception happens. Now we don't use yield or in this case, we use bracket P because bracket P actually knows how to work with the resource T bit. So bracket P is going to go ahead and say, hey, let's acquire some resource, let's clean it up, and in between, map M yield. And people who are familiar with writing exception safe code in Haskell with bracket, the with binary file function, for example, you're already used to this pattern. So you're able to just go ahead and use it. Yeah.
Is there a reason not to use this by default?
Use what?
Use run conduit res by default.
If you don't, so should you not use run conduit res by default? If you don't need the resource T, then it's extra overhead. It has a small, tiny runtime overhead. It makes more sense to just stick to the types that you actually need to be explicit. Odds are, if you're doing anything, if you're dealing with a file at any point, you're going to need this. So almost all pipelines that are doing some kind of I/O end up needing something like this. Actually, there is one other possibility. If you already have a resource T block that was already established beforehand, then you can reuse it, but that's slightly more complicated. Okay. Okay, just a little bit more details on this. The reason why resource T exists is because, and this is getting a little more technical, when you have a coroutine or a continuation passing style concept, there is no way to safely do exception handling. This applies to lots of different monads, actually, not just to Conduit. It also applies, for example, to the continuation T, the cont T type in transformers. You cannot do proper exception handling from that transformer. However, if you use resource T together with cont T, then you are able to go ahead and safely deal with exceptions. Also, there are some use cases where resource T is the only way to efficiently do this. A good example of this is a deep directory traversal. Let's say that you're going to go inside a directory multiple layers. Each time you go into another layer, you're going to have to grab hold of a new directory handle, and you're going to have to register an action to close it up. If you were just using the with binary file kind of approach, the bracket kind of approach without resource T, going into these deeper layers wouldn't work. You wouldn't be able to just get hold of one of these handles, say, outside of the Conduit pipeline, and then use it inside, because you're traversing all of these different layers. So instead, with resource T, you can dynamically grab onto more resources that you need to hold onto, and then release them. Okay. I actually, in the applied Haskell talk earlier this week, we looked at average. This is another way of doing a bad average in Haskell. We're going to go ahead and we're going to yield the numbers 1 through 10. And then we're going to use applicative syntax. I hope everyone is a little familiar with this. But essentially what it means is we're going to apply this function divide to the result of sum C and the result of from integral length C. So sum C is going to go ahead and it's going to take the numbers from 1 to 10. It's going to add them all up. And length C is going to figure out how many values there were, which is 10. And then it's going to divide these two things, and it's going to come up with our average. This doesn't work at all. Can anyone take a look at it and guess why?
Does length C not get anything?
Does length C not get anything? Yes. Why not?
Sum C ate it all.
Sum C ate it all. That's perfect. Sum C is going to go ahead and it's going to consume the entire stream. It's only going to give up when it's done, when there's nothing left upstream. By the time we get to length C, we can't consume this. This is your question earlier. Can we consume things in parallel? Well, with Conduit by default, you can't consume things in parallel. You can't have two things working off of the same stream. However, we have something called a zip sync. This is modeled off of the idea like a zip list. You're able to work on two things at once. It's just a new type wrapper. We are applying zip sync to sum C, zip sync here, and then we do get zip sync. And this does exactly what we want. It runs both of them until both of them complete. It returns the value from them, and then we're able to just divide the value, and it all works. Cool. Also, I just want to point this one out. This is one of those cases where you could actually kind of argue that Conduit's better than lists. I showed an example. I can show it to anyone who wants to see it later. There's a very common example of a space leak that you make in Haskell by just dividing when you're doing sum and length over a list. And it holds on to both lists. It holds on to the list in between the two computations. When you deal with Conduit, it's actually forcing you to avoid doing something like that, because it's forcing you to deal with it as a stream. It never will allocate an entire list in memory to hold on to that to all those values.